Here, now we discuss types of functions. I am considering 4 types of functions, 4 kinds of functions. Namely, number 1 is 1-1 function. I have denoted this by my symbol 1-1, which is also called injective mapping. Injective means 1-1 and mapping means function. So 1-1 function means injective mapping. Another function is many-1. A function which is not 1-1 is called what? Many-1 function. There are 4 kinds of correspondences that we have seen. One is 1-1 correspondence, 1-many correspondence, many-1 correspondence, and many-many correspondence. Among these, only 1-1 and many-1 correspondences are functions. 1-many and many-many are against the definition of functions. Hence, there are only 2 kinds of correspondences which are functions, namely 1-1 correspondence, which is called 1-1 function, and many-1 correspondence, which is called many-1 function. So, if function is not 1-1, it is many-1. If function is not many-1, it is 1-1. Another thing is what? Onto function, which is also called surjective mapping. So, onto means surjective. Function means mapping. So, onto function means surjective mapping. If function is not onto, then it has to be what? Into. So, there are only 2 kinds of thing as far as onto-ness is concerned. Either it is onto or what? It is into. Let's see in detail what is 1-1 function, many-1 function, onto function and into function. Look into these 2 examples. Here are the 2 examples to illustrate these concepts. Let's look into the first one. F1 is a function defined from the set A to the set B. This is the domain of the function. This is the codomain of the function. A, B, C, D are the elements of the domain. Now, every element in the set A is related with 1 element. B is related with 2, C is related with 3, and D is related with 4. Once A is related with 1, no other element will get related with 1. This is the concept of what? 1-1 function. So, every member of the set A has unique image. So, if 1 is the image of A, 1 cannot be the image of any other element of capital A. If this happens for all these elements, we say that function is 1-1. So, there is a 1-1 correspondence. To understand this in a better way, let's look into the second function F2. Here, I see that A is related with 2. But at the same time, you can see that D is also related with what? 2. So, 2 is not only the image of A, but 2 is also the image of D. Means, here 2 distinct elements of capital A are related with what? The same element. Hence, this function cannot be said 1-1 function. A function which is not 1-1 is what? Many-1. So, this is the example of many-1 function, and this is the example of many-1 function, and this is the example of what? 1-1 function. So, there is a 1-1 correspondence between the elements of A and B. So, function is what? 1-1. One can see this definition in another way. A and B are not same. That means their images f of A and f of B. Are they same? What is f of A? Here actually it is f1. So, f1 of A is how much? 1. So, this is equal to 1. f1 of B is how much? 2. So, this is 2. So f1 of b is 2. Because a and b are different, their images 1 and 2 are also different. Therefore, if this condition is happened for any two members of capital A satisfied by f1, then we say that f1 is 1, 1 function. So in general, I would say that if x1 and x2 are any two elements of capital A such that x1 is not equal to x2, then in order to get the function 1, 1, this should imply f of x1 is not equal to f of x2. And if this happens for any two distinct elements of capital A, we say that function is 1, 1. So this is the way, one way of checking function is 1, 1 or not. Choose two elements of capital A which are distinct. Find their images. They should also be distinct. If this is the case, function is said to be 1, 1. On the other hand, if I say that f of x1 and f of x2 are same, then for 1, 1ness, it is necessary that x1 and x2 are also same. Therefore, if these two elements become equal, then these two elements are to be also what? The same, in order to have the function what? 1, 1. So I can say that if f of x1 and f of x2 are equal, and if that implies x1 equal to x2 for every x1 comma x2 belongs to what? Capital A, then we say that the function f is 1, 1. There is one concept in logic that if I consider P is one statement and Q is another statement such that P implies Q is there. Now, P implies Q means if P then Q, then it is equivalent to the fact that not Q implies not P. Here, not Q means what? Negation of Q. That any statement is given as Q, and if I negate it, means if I put at the proper place the word not, suppose man is rich, then what is the negation of that? Man is not rich. Such kind of statement this is. So if P then Q, then this is equivalent to not Q implies not P. So I am interchanging the positions and I am changing the signs. I am making it what? Negative. If this is the case, these two statements are what? Equivalent. This is exactly which holds in logic. It is here. F of x1 equal to f of x2 is P, and this implies x1 equal to x2 for every x1 comma x2 belongs to A is Q. So this P implies Q is same as, what is this? This is, if I say this is P and if I say this statement is Q, this is exactly negation of Q and this is exactly negation of P. So P implies Q is equivalent to not Q implies not P. So whether I consider this case or this case, both mean one and the same, that function is 1, 1. So in order to show that function is 1, 1, consider values of the function at x1 and x2. Any x1, x2 belongs to A. When values of the function are same, then x1 equal to x2 means these are the images of x1 and x2 and these are the pre-images. So whenever images are equal, pre-images should be equal in order to get the function 1, 1. So this is the description which tells us what is a 1, 1 function. Even through this example, we have seen that how the function is 1, 1. So this is the example of 1, 1 function. This is the example of many 1 function. Now let's try to understand the next concept, the concept of onto function. A function f from the set A to the set B is said to be an onto function or surjective mapping. You need to find range of the function. This is the codomain of the function and this is the range of the function. Let us recall what is the range of the function. It is the set of all those y belongs to B. I am collecting members of B such that they are related with x under the function f, where x comes from what? The set capital A. If this is the case, then such a set is called range of the function. Now, a function f from A to B is said to be onto if the range of the function is equal to codomain of the function. Now, very clearly, whichever elements I collect in this set are essentially the elements of B. So, every member of this range of the function is a member of B. So, naturally, range of the function is subset of B. Now, we know that two sets capital A and B are said to be equal if they are subsets of each other. So, by default, range of the function is subset of B. So, if I could show that codomain B is also subset of the range of the function, I would have shown that range of the function is same as codomain of the function. So, whenever range is equal to codomain, we say that function is onto. Let's see whether in this example this function is onto or not. If I want to find the range of the function f1, I must collect the elements of capital B towards which the arrows have come. So, 1, 2, 3, 4. These are the elements towards which the arrows have come. So, if I collect here all these members in this set 1, 2, 3, 4, we see that the range of the function is a proper subset of the codomain. Can I form one set like this inside? So, we see that there are still members in the set B which are not related, namely 5 and 6. So, whatever set RF I am getting, it is a proper subset of B. Proper subset means what? You can find in the set B, at least one element which is not present in the set RF. So, if RF is a proper subset of B, you should be able to find at least one element in the set B which is not present in what? Range of the function. So, this is exactly happening over here. So, one can say that range is a proper subset of B. Hence, every member of B is not an image of the elements of capital A. So, we say that this is the example which shows it is not an onto function. A function which is not onto is called into. The name may have been given in this sense that whichever range I find, if it is sitting inside the codomain B, we say that function is into. So, it is going inside completely. This is completely within B. So, we say that function is what? Into. Look into this. In this example, do you see any element in B which is not related? In the set B, 1, 2, 3, these are the 3 elements and every element is related. Therefore, if I form the range of this function RF2, it is 1, 2, 3, which is exactly equal to B. So, whenever range of the function and codomain are same, we say that function is onto. So, this is the example of the function which is what? Onto. So, because here no element in B is left to get related, therefore, we say that function is onto. Here 5 and 6 are not related, therefore, the function is into function. So, this is 1, 1 and into function, and this is many 1 and onto function. So, here I have produced 2 examples which are showing 1, 1 and into, and another example is many 1 and onto. So, whenever we want to show that function is onto, what you do through the analytical method, you choose any y in B. For that y, you find x in the set A such that the relation f of y equal to f of x holds. So if I could find for every y 1x in capital A such that y equal to f of x, we say that function is onto. If function is not onto, it is just into. So this is all about one, many one, onto and into functions. I hope you have understood this.